We now consider the speed of waves. The speed of a wave depends upon the medium because of the interaction between the particles that create the propagation of the disturbance. Now, in general, we can say something about, at least for mechanical waves. So for a mechanical wave, we can tell you that the speed, v, is related to the square root of something related to the force. We'll call it the elastic force factor that connects the various oscillators, divided by an inertia factor, that is, the desires of the oscillators not to accelerate. Now, what this specific force factor is, an inertia factor, will depend upon a particular type of wave, but they will all have this type of form, square root of something related to force and something related to inertia. Now, let's first consider a transverse wave on a string. In this case, the speed depends on the square root of the tension, which represents the force factor, divided by the mass per length. Now, these are generally given the following symbols: T for tension, and on the bottom mu, where mu is defined as mass over length. Again, notice it has a square root. Notice that there's a term here related to the force and a term here related to inertia. For number 2, we'll consider the example of a longitudinal wave on a solid rod. And let me add a new page here. So in this case, we again have v, and for the square root, we have force divided by density. Now, different books will use different things. By this, I really should say linear density. This is a one-dimensional example. So what we're talking about is the square root of F for force. And depending on the book, they'll either use rho or they'll use lambda, but it is linear density. A third type of problem that's common is to look at a longitudinal wave in a gas or solid. And again, we have the square root. In this case, for a longitudinal wave, the force factor is called the bulk modulus, which has the units of a pressure. And on the bottom here, we have again density, but this time it is the volume density. And this is usually written as the square root of beta for the bulk modulus and rho in kilograms per meters cubed for the total density. As an example of such a problem, let's go on now and look at the second fact And the second fact is that when a wave goes from one medium to a second medium, its speed and wavelength change, but not its frequency. So remember, we have the relation that speed is equal to lambda f. And so if it goes into a medium where this increases, then lambda also increases. Faster means that it'll have a longer wavelength. So if the wave picks up speed as it goes from one medium to the second, then it will also have a longer wavelength. If it slows down, then it'll have a smaller wavelength. So let's look at a problem for this type of material. So as an example, a whale emits a wave of 2.0 times 10 to the 5th hertz in seawater with bulk modulus of 2 times 10 to the 9th Newton per meter squared, and density of 1.025 times 10 to the 3rd kilogram per meter cubed. What is the wavelength of the wave? So in order to find the wavelength, since we know the frequency, we first got to find the speed. The speed is equal to the square root of the bulk modulus over the density, which is the square root of 2.0 times 10 to the 9 Newton per meter squared, divided by 1.025 times 10 to the 3rd kilogram per meter cubed. And if you do the dimensional analysis, you have a kilogram meter per second squared. So this thing here will kill all but one of those meters. The kilogram meter per second squared, the kilograms will cancel, and you'll be left with meters squared per second squared. Take square root, you get meters per second. 10 to the 9th over 10 to the 3rd gives 10 to the 6th. Square root of that will leave us 10 to the 3rd. And we have 2 divided by 1.025 and take the square root. When I do that, I get 1.40. So 1.4 kilometers per second is the speed of the wave. Lambda, the wavelength, is the speed divided by the frequency. So that's 1.40 times 10 to the 3rd meter per second, divided by the frequency, 2.0 times 10 to the 5th per second. Punch that in, and I come up with 7.0 millimeters for the wavelength, or 0.7 centimeters. So a fairly small wavelength. So you can combine the properties, find the speed from the properties of the medium, and use the fact that V is lambda f to relate the wavelength and the frequency. Remembering that the frequency of a wave does not change when it moves between media, but the wavelength and the speed of the wave does change. All right, we'll see you in another video.